Right, this is for the section on simple harmonic motion. I already covered most of this in my first video about this, but there's a couple of things we need to add on that we're talking about that. First, if you take the equation, and it takes some time, so I'm not going to show it here, a sine omega t for position, and the equation for omega a cosine omega t for velocity, you can actually combine these to eliminate time. So you have to go through and solve for time, and then go through and solve for time and substitute in the other one, and you'll end up getting that velocity is equal to plus or minus the angular frequency times the amplitude squared minus the displacement squared. And of course in your data booklet they don't use amplitude, so it's plus or minus the square root of x naught, the initial displacement, which is the amplitude, minus x, because it never goes below that. So the initial displacement is the maximum, so that's what they have there. The other little thing to add on is simply that the total energy in simple harmonic motion comes from 1/2 mv squared, and the basically the maximum energy then occurs, actually I should just say the maximum potential energy, no, what am I saying? Just this maximum occurs when we've got the biggest part of this 1/2 m omega squared at the amplitude squared, because v is omega times r, however far out you happen to be. And again, in the terms of the in terms of your data book, it's omega squared x naught squared instead of amplitude. And then we can do the potential energy. Similarly, if we're not out at that amplitude, 1/2 m omega squared then x squared. And then that's not in your data booklet, but we still should kind of know it. And then the kinetic energy, which is given to you in your data booklet here, is going to be just the total energy minus that, and you'll end up getting minus the potential. You get 1/2 m omega squared amplitude squared minus displacement squared, or with the x naught, 1/2 m omega squared x naught squared minus x. Okay, and so that's pretty much it for what needed to still be said from simple harmonic motion that I didn't cover in the other videos. Pretty simple, just this equation and then the kinetic energy and potential energy equations right here. Right, and now let's move on to what I in the next video, what I have to do for the next topic, which is some more detail on single slit diffraction. So let's go ahead and just do that. So we'll do single slit and a little more detail here, the diffraction pattern. We're not going to do, diffraction, single slit diffraction pattern. So as I discussed in the previous video, you have a slit, screen very far away, and you get some sort of pattern like this, where that central one is really bright, and then they trail off like that. I really shouldn't, my slit needs to be more central over this. And then what you'll have is, we'll name the slit width, the width of the slit, we'll call it B. We're going to just go ahead and name, just so we can talk about it, the width of the central one, we'll call it W. And the first property we should notice is that W, the width of this central bright, is going to be greater than B, because as the light comes through, it diffracts outward, right? So it is going to widen out as it does this. I want to name the angle theta, so if we come straight down here, theta is going to be the angle subtended by the by these maximums. This would also be another theta, and every time you go out across another one of these brights, they're theta. which means this central one is actually twice as wide as any of these other ones, so it's a theta, and it has a total of 2 theta. Okay, and we can calculate theta. I'm not going to go through the whole derivation of this, but you could look it up if you're really super interested. Is just the wavelength over the width of the slit, and that will give you this angle theta. So slit width and wavelength. And so as you can see, as the wavelength gets bigger, this is going to spread out wider and wider, and that's kind of important when we talk about resolving images in a bit. So some of the things you should notice is that the central bright fringe is wider than the slit, so I had already written that down. It's wider than the slit. I said that here. The central bright fringe is much brighter than the others, than all the other smaller order fringes. After the central bright fringe, each consecutive fringe, so consecutive fringe, that's not counting the first one. There's a big drop after the first one, but then after each of these, they tend to cut in consecutive fringes after the middle one, reduce in brightness by about a half. So I think they say a little brighter than half of it, but they cut down about half. So this one's this one's half as bright as this one's half as bright as that one. It just keeps going down by halves. So about half as bright. And then the last thing, no, I think that's, yeah. Oh no, the last thing is that the central fringe is twice as wide as the other fringes. So this is W. That makes this one would be 1/2 W, or W over 2, W over 2. These would all be W over 2 in width. Okay, so they get smaller as you go out. Okay, I think that's pretty much everything I needed to add on that I hadn't already covered for those sections, and this should pretty much get you through it. There's not a lot to them other than that, and just using this stuff. Okay.